Heat rates. Broadly speaking, the term heat rate function might refer to the marginal or average heat rate function. Both are derived from the heat input function. The heat input function is given by the shape y is a function of x, where y is the heat input or the amount of fuel consumed to produce at megawatt level x for 1 hour. The marginal heat rate function is the derivative of the heat input function. The average heat rate function is f of x divided by x. The heat input at a notional 0 megawatt output is referred to as the no-load cost. Heat rate can have more than one shape. It could be a polynomial equation with a base value and coefficients correspond to each term. It could have a load and the heat input corresponding to it. So each load point will have a corresponding heat input and average heat rate. In PLEXOS, the heat input function is input as a polynomial function. So y equals a plus bx plus cx plus square plus d x cubic. The term a, which is the intercept of the heat input function with the y-axis, is the heat input base. The b linear term is the heat rate increment, while c is the quadratic term or the heat increment 2, and the optional d term is the cubic or heat increment 3. The no-load is the constant term in fuel used function or the no-load cost. It's preferable to have a convex heat rate, so the definition of a convex curve corresponds to any points on the line can be connected to another point without going underneath or below the line. The implication is that the marginal heat rate curve is monotonically increasing, so the next megawatt hour always costs more fuel to produce than the previous one. As a summary, in PLEXOS, we can define the heat rate as average, the heat rate increment is a marginal, heat rate base is the no load, and the heat rate increment 2 is the quadratic term, and the heat rate increment 3 is the cubic coefficient in the polynomial equation. And finally, the load point is the generator load. Heat rate modeling. So properties used could be linear, polynomial, or pieceline linear. If we're using the linear approximation, we have the heat rate or heat rate increment, heat rate base, and heat rate increment. In the polynomial, the first term will be linear, which is the heat rate base and the heat rate increment. The quadratic will be the heat rate increment 2, and the cubic will be heat rate increment 3. If we are modeling using the piecewise linear, so we'll need to have a corresponding heat rate for each load point, a heat rate and heat rate increment for the load point, and heat rate base and increment for the load point. Examples of heat input function. We can use the constant, so the average equals the marginal heat rate. In this case, we see that the heat rate has a single value for this generator of 9 gigajoule per megawatt hour. If we are using the quadratic heat input, we need to specify the heat rate base and the heat rate increment and the heat rate increment 2 coefficients, all coming from the polynomial equation. And finally, if we are modeling using the marginal heat rate with no load cost, we need to specify a heat rate base and increment for each load point. In this case, we use different bands in PLEXOS. So load point of 50 megawatt resides on band 1, and on the same band we have heat rate base of 3 gigajoule per hour and heat rate increment 8 gigajoule per megawatt hour. The load point 100 megawatt resides on band 2, and that corresponds to the heat increment 8.2 gigajoule per megawatt hour, and same for 3 and 4.